These next few slides show some NMR spectra along with the structural formula that they correspond to. So this is designed to get you used to looking at the graph itself and associating it with certain chemical structures. Eventually the idea will be, if you know what atoms are in a molecule, the NMR can be used to figure out how everything's connected, what class of compound it is, and the details of where all the carbons and hydrogens and oxygens and so forth, how everything's connected. But for the time being, these examples show you both the structure as well as the spectrum that goes along with it. Anyway, we'll start with a simple spectrum, and this is as simple as it gets. A single peak here with a chemical shift, as it says, of around 2.2. Now, if all I had to go on was just the graph, I couldn't automatically tell you what molecule this corresponds to. So I would need some other clues. But I could tell you that no matter how many hydrogens that molecule has, they are all equivalent to each other. And as it says here, this corresponds to acetone or propanone. All 6 of these hydrogens that are highlighted here are equivalent. They're both part of methyl groups that are attached to the same carbonyl, so they should give rise to a single signal or a single peak in the spectrum. And if you look back at that correlation chart, the fact that this is just a little bit over 2 on the parts per million scale, that kind of chemical shift certainly is consistent with hydrogens on a carbon adjacent to a carbonyl. So at least that does make sense. Here's another fairly simple case. We've got 2 different kinds of hydrogens here. The red hydrogen is associated with this peak around, looks like 9.7 or so, 9.8. And the blue highlighted hydrogens are associated with this big peak over to the right, centered around 2.2. And what's labeled here, the 3H and the 1H, is telling us the number of hydrogens to associate with each peak. And that's something that's really nice about NMR, is that when you have different hydrogens or different sets of hydrogens, the size of the peaks are proportional to how many hydrogens are giving rise to that signal. So that can be very helpful, especially if we have a number of different peaks and we're trying to associate each peak with one or more hydrogens in a molecule. The fact that we get a resonance almost at 10 is certainly consistent with an aldehyde hydrogen. And just like we saw with acetone in the previous slide, when you have hydrogens on a carbon next to a carbonyl, we expect that resonance to be a little bit over 2 parts per million. And the fact that, again, these are in a 1:3 ratio tell us that the aldehyde hydrogen, there's only one of those, and it's again, a part of the same molecule where we have another group of 3 hydrogens that are all equivalent to each other. And generally speaking, hydrogens connected to a single carbon will give a single peak in the NMR spectra. It's not always true, but it certainly will be for most of the examples that we see as we go along. What's actually being calculated when this is run by a computer is the area underneath these peaks. They look like single spikes, and sometimes the peaks will be broader, and it's not just how tall they are, it really is a matter of the area that's encompassed by the peak. But that's done by the NMR spectrometer, and so that kind of information is given to us when we're trying to, again, work through examples like this. Here's an example from the textbook, figure 13.12, and you can see they've color-coded the hydrogens here, and we've got 2 hydrogens, part of that CH2 group, that are equivalent to each other, and their resonance is different from the group of 3 hydrogens on this methyl group. Both of those sets of hydrogens are near that oxygen that separates those 2 carbons, which is why their chemical shifts are where they are, a little bit higher than what methyl groups typically resonate at. But again, that's consistent with that structure there. And again, the 2H and 3H is telling us that these are in a 2:3 ratio by their area, which allows us to also associate the correct peaks with the correct hydrogens, the smaller peak being created by the smaller number of hydrogens. Here's another example from the textbook. This benzene ring here, that's the 6-membered cyclohexane ring with the alternating double bonds. That shows up a lot, and even though there are 5 hydrogens that are implied on this ring, they give rise to essentially a single peak there. Sometimes they are split in a more complicated fashion, but the fact that they're resonating a little over 7, around 7.3 parts per million, that's very commonly going to be the case when you have one of these benzene rings. And as it says at the bottom, these are in a 5 to 2 to 1 ratio, which also helps us assign the right peak to the right part of the molecule. The blue hydrogens, the CH2 hydrogens, they are again giving rise to a smaller peak since there's only 2 hydrogens there. Alcohols like this OH hydrogen, they can show up anywhere along the chemical shift scale, but they do give single peaks, and oftentimes they're a little bit broader than some of the really sharp peaks that we associate with other hydrogens that are connected to carbons oftentimes. Notice this also reminds us that TMS, tetramethylsilane, is our reference peak that we are relating everything to, and when that shows up, it should necessarily be at 0.0.